Hello friends, welcome back to my channel. And in today's video, we are going to look at time complexity and space complexity in machine learning, deep learning, and AI algorithms, and why it's important. Now, understanding and measuring time and space complexity is very important for building efficient, scalable, and production-ready machine learning and AI systems. So you see these terms thrown around a lot in the field of machine learning and AI. So we're going to look at how or why it's even important in the first place. But before then, let's look at a few definitions. So I have a table here with the aspect time complexity and the space complexity on the last column. So as far as the definition, time complexity is about how the runtime of an algorithm grows with input size. So let's say you have an algorithm that is currently running with an input that has a size of, let's say, 100,000 data samples. What happens to the algorithm or the runtime when we increase the input size to, let's say, 100 million? So that is a problem that falls under time complexity. For space complexity, we are talking about resource usage. So how the memory usage of an algorithm grows with input size. So the way computers work, or when you're doing mathematical computations with a computer, it's always faster if you are able to load all your input data inside memory. In that case, we measure memory usage that the algorithm demands based on us increasing our input size. Now, as far as what it measures, for time complexity, we are measuring CPU time, or the number of operations or steps, which is also known as flops, floating point operations. And the space complexity, we are looking at RAM usage. For RAM usage, we are talking about number of variables, arrays, basically data structures. When it matters. So time complexity matters when performance or throughput is very important in our algorithm or in our computation. And by throughput, I mean the number of data packets that arrives within every second. Okay, that is throughput. For space complexity, we are looking at when we are working with limited memory or a large data or model. Now, a typical example is, let's say, when we train a linear regression model on 1 million samples. This type of modeling problem falls under time complexity. But when we talk about storing the learned coefficients of that linear regression model, which is also known as the beta variables, storing them, we are looking at space complexity. So the key limiting resource for both of them is the CPU and GPU compute time for the time complexity and the RAM or VRAM for the space complexity. So I have an analogy here that you can use to understand it easily. When you talk about time complexity, think of how long it takes to cook a recipe. When you talk of space complexity, think of how many ingredients and utensils you need in your kitchen to cook that recipe. Now in the next few pages, we will look at why time complexity and space complexity matter. I'm still a young channel and I'm trying to grow, so please like, comment, and subscribe to my channel for more videos like this. And now let's get into it. All right, so we are going to look at a few situations and classify them under time complexity or space complexity or both. Real-time predictions. Now this is like streaming data, where you're analyzing some data with some model or algorithm, and new data is constantly coming in. In that case, time complexity is very critical. Space complexity is also important. Even though it's important, time complexity is more so critical because you're dealing with real-time predictions, right? For instance, if you have an edge or IoT device, something like a self-driving car, see that a self-driving car is not always plugged in. You don't see it, but it's actually running some code in the backend. In that case, the computer that is inside the car should have enough memory and processing power to compute. You see, usually self-driving cars have cameras around it that is constantly taking photos or videos, and those are cast into matrices that the computer tries to solve or compute. Space complexity is really critical for edge devices. And it's not just self-driving cars. Let's say maybe a computer that scientists may take to a place like Antarctica, where they can plug into supercomputers elsewhere. In that case, space complexity is very important. Now, if you think of distributed training, in this case, the compute cost is important. In that case, both of them are critical. Also, debugging slow pipelines or memory leaks, both of them are really helpful for solving this kind of problem. So both should be analyzed before scaling or deploying any machine learning model. Now, usually machine learning engineers or MLOps engineers do this before they deploy any model. I'll expand on this in a couple of slides here. So first is scalability and performance optimization. Now, in real-world ML systems, datasets can be millions of rows and hundreds of features. So a model that works fine on a small data may crash or take hours on a large data. So time complexity tells you how the model's runtime will scale as the data size increases. Let's say from 100 to 1,000, from 1,000 to 10,000, 10,000 to 100,000 to a million. You try to see how the model's runtime actually works. Now, this helps you to choose between algorithms. Should you use linear regression or XGBoost? Should you use decision tree or random forest? And this is decided based on the workload. So let's say a model with training time complexity of order n squared may be fine at 1,000 samples, but fail at 1,000,000 samples. Now I'm going to explain this O here. In mathematics, we call this the big O. So this just tells you how much the runtime of your algorithm increases as data grows. So this means that as the data or your input data grows, this algorithm that we are using to train this model here is going to be increasing quadratically. So that's basically the order of the runtime. Next, the second point here, you have efficient resource allocation. And that's either you're using the cloud, GPUs, or let's say you have a CI/CD. Now on cloud platforms like AWS, GCP, and Azure, they all charge based on CPU or GPU, and some on RAM. So time complexity helps to estimate how many resources you need for training a machine learning model or for inferencing from the machine learning model. It also helps you to not over provision or under provision. Sometimes you may need just an EC2 instance, but because you don't really know the time complexity of the model that you're trying to deploy, you over provision it, that's going to be costly. Or sometimes you may also under provision it, which will cause the model or the deployment to crash or to slow down. So ML and MLOps engineers often have to choose the right VM types, the training schedules, or the auto-scaling rules based on the expected compute load. You should be able to know all this. Next point, we have model deployment and latency targets. Now there's a slight difference between throughput and latency. Throughput is just the number of data packets that arrives every second. Latency measures time, how much time it takes for a packet of data to be transferred. That is latency. With that, we can say that in production, let's say you're running a real-time system, then the inference time must meet latency SLAs. And these SLAs are very common in site reliability engineering. So knowing inference complexity helps you to optimize the model size, the feature count, as well as the hardware needed, whether you need GPUs or you need CPUs. It's all up to inference complexity of your model. Now, if you fail this, that can mean that your users are going to have a very poor experience interacting with your model, which would lead to loss of revenue, most likely, or your API can time out because maybe you needed GPUs to run this workload, but you're using CPUs, and so it's not very efficient. Another reason why is pipeline bottleneck identification. Now, in a lot of MLOps pipelines, even in AI as well, you have multiple stages. You have a stage where you ingest the data, you pre-process it, make it ready for training the model, and then you train the model. After training the model, you validate it to check the accuracy and other metrics to determine whether your model is good or not, and then you go from there to deploy it. So in case your training or the model is slow, it may be due to the data size, the feature dimension, or the model type that you're using. It could be any of these three or even more. So time complexity can tell you where the bottleneck is, what is causing it to be slow. And then from there, you can actually fix the problem. Okay. Next is algorithm and architecture decisions. Time and space complexity helps guide design decisions. So you would ask yourself, should we use a mini batch training? Or if the data is too large, are we going to need to do dimensionality reduction? Now, dimensionality reduction is just, so imagine we have a data that has 100 million rows and then let's say 100,000 columns or features. But we don't want to use the whole thing to train the model, right? So we can use some dimensionality reduction techniques to reduce the size of data that we need to use to train the model so that the computation doesn't take too long or doesn't cost us too much money because of the CPU, GPU, or the RAMs. You can ask yourself, is online learning more appropriate? Now, online learning is just the method where a model learns from data sequentially, basically one data point at a time. That is how the model learns. So it's like you drop a coin in a machine and then the machine uses it to learn something. You're not using static data. So from time to time, new data point, which is a single data point, drops in and then the machine learns from it. And then another one comes and so forth, right? Do we need to use that? That is also a question that time complexity or space complexity can answer. So analogy here for streaming or real-time applications, linear models with an order n.d might be preferable to deep models with order n(d squared). Now, n is the samples or the number of samples you have or the number of rows in a table, and d, we usually use that to represent the features that you have in the data set. So in linear models, this order may be preferable to this quadratic order. Next, we talk about debugging unexpected slowness. Now, if a pipeline suddenly becomes slow, then your complexity analysis is going to help you to distinguish what's actually causing the problem or what is not. Is it because of the data growth, or is it because our code is inefficient? Because time complexity also helps you to write efficient code. Okay. Is it from algorithmic flaw, or is it an infrastructure issue? So it is helpful during model retraining, especially when you are dealing with evolving data sets. Another point or another reason why it's important in ML or MLOps is documentation and communicating trade-offs. So time complexity serves as technical evidence when presenting model choices to whoever, stakeholders or product managers, MLOps or DevOps teams. So you need to explain why, let's say, a logistic regression model is best compared to, let's say, a random forest model, even though both of them may have similar accuracy score or pretty much almost all the metrics look similar, but then you pick one over the other. You need to justify your reason why. So you can say, let's say model A takes 2 times longer than model B on 100,000 samples. Just by being able to answer this question, you pretty much save the company a lot of money because they would have had to pay twice as much by using model B. So you have to pay for more compute and more RAM space. And so this saves stakeholders a lot of money. So that's also the reason why it's important. Another point we have here is foundational skills for advanced topics. Now, if you get the idea of time complexity and space complexity, you can easily build on it to actually write better algorithms. You can build on that to learn distributed ML like Harvard or Ray, other ML systems, model parallelism, and data sharding, MLOps orchestrations like Kubeflow, Airflow. You can easily build on that to learn these kind of skills that are becoming very important in the field of machine learning, MLOps, and AI. In computing, there's this quote that you hear about it a lot, and it says, if you can't measure it, you can't manage it. So if you're running an algorithm on a compute resource, let's say some supercomputer, if you can't really measure how much compute you are using by running that model on that system, then you can't really manage it. Okay, so you always keep this at the back of your mind. And in order to answer the question of measuring it, you need time complexity, space complexity. So as an ML or MLOps engineer, understanding time complexity will help you to build faster, cheaper, and more scalable ML systems. So on these few slides, I have a table with the time complexity and the space complexity of some common machine learning models. Now for the time complexity, I have two different columns. One is for training the model, and the other one is after you've trained the model, if you are trying to use it to predict, that is inferencing, that also has a different time complexity. So linear regression, the closed form linear regression is basically linear regression with OLS, ordinary least square method. For that, the training time complexity is of the order n times d squared plus d cubed. So it has cubic order. Now usually the d is for the features and the n is the sample. So I actually have the terminologies here for each of the variables that you see in the previous page. Okay. So d is the number of features or inputs dimension. N is the number of training samples. K is the number of epochs or iterations. H is the number of hidden layers. This is for neural networks. T is for the number of trees, and this is for ensemble methods like random forest. I is for iteration, say for k-means. NSV is the number of support vectors, and this is for support vector machines. C is for number of output classes, and K is for the number of PCA components. Now this is not for the k-means, this is for PCA components. So let's go back to the previous table again. You can go through it, look at the training time complexity, the inference time complexity, and the space complexity for each of these models. Be on the lookout for those videos. I'll try to do them one by one about calculating time complexity of these different machine learning models in subsequent videos. Now, if you have any questions, keep them in the comment section below. I'll also add a link to this PDF file that I'm using so that if you want to go through it, you can also do that. Thanks again for joining me on this video. So I'm still a young channel and I'm trying to grow. So please like, comment, and subscribe to my channel for more videos like this.